Welcome to Lesson 3-2, Deviations, Residuals and the Correlation Coefficients. So the objective of this lesson is to calculate the sum of the squares of the residuals, the sum of the squares of the residuals S res, and find out how to determine the equation of the line or the linear function that minimizes S res. In Lesson 3-1, we have proven, or we have introduced you to the hypothesis that when the S res is minimum for a given linear function, which is y hat, then that equation of linear regression is the one that best fits the line. Therefore, that should be the best fitting linear function equation for a given data which is scattered. Okay? So simultaneously, for lesson 3-1, we were talking about this workout of Mo, who had an injury, and upon feeling that he has this feeling of recovery, he recorded his number of days and the number of sit-ups that he can do for that particular number of days. So in 2 days, he got 8 sit-ups. In the 4th day, he got 10 sit-ups. In the 6th day, he was able to make 19 sit-ups. And on the 8th day, 18 sit-ups. On the 10th day, 25 sit-ups. So because our range, or the interval within which Mo did the sit-ups, were from 2 days to 10 days, the sum of the number of days is equivalent to 30 days. Am I correct? So meaning it is like a month of testing his recovery. Okay? And the number of sit-ups that he did totals to 80. Okay, so there are 80 sit-ups. So what is very keen here is that the average or mean of the y values would be taken as, now we could take the average of this by getting the sum of all the sit-ups. So our sum actually is 80, right? So sum divided by the number of events. So how many events are there? We have 1, 2, 3, 4, 5. So therefore the sum is 80. Number of events is 5. That gives us 80 divided by 5, or that's equal to 16 sit-ups on the average. Okay, so for this 5 data that he performed the sit-ups, the average of one of one of these performances would equate to 16 sit-ups. Okay, and then now let us graph the mean of the number of sit-ups that Mo did. So the number of sit-ups is an average of 16, which is here, this line. Okay, the average is this line, the red line. And these are the points of the data with most performances with the sit-ups. And as you can see, if you get the values of y from the mean, so for the first point and for the first y value, our y value here is 8, right? So from the mean going to the value of 8 of y, which is 8, and this is 16, the residual here could be taken as this one, 16 minus 8. Okay, so clarifying, this is our mean. Okay, this is our mean value for each of the events that he did the sit-ups. Now this one is our deviation. The y values here are our deviation. Okay? So y minus y bar, or that's the mean, is the deviation from the mean, right? Because this is our mean, so the deviations from the mean are taken when we get the difference between y and the mean. So this is the deviation from the mean, okay? You got it? So these are deviations. These are deviations from the mean. Okay? Now, what is so important here is that the deviations from the mean, if we take the mean as a horizontal line, you can see that the deviations are far, far away from the mean. Now, there is a better way of solving a given, a better linear function or linear equation for this one. And that is by assuming that your y is a linear function of x, meaning y is equal to a linear function of x, so something like ax plus b, right? So y now is a linear function, it's a function of x, okay, meaning that it should be a straight line. So in doing that, we could actually put a line that somehow, best fits these given points. Okay, so we drew this line, okay, this line, the violet line here. Okay, so if we take a slant line instead of the horizontal line here, now we could see that the deviation from this line became smaller. Okay, and we call these deviations, not deviation. If a while ago we have the deviations from the mean, now we call this deviation as residuals deviation, or deviation from residuals. These deviations, okay, these are what we call residual deviations. And what do you mean by residual? As we have introduced, residual in terms of algebra or variables is y minus y hat, okay, for this standard thing here. So if y hat is the value of y for a point on the line, so this is our line, okay, and if these points here, these are the points, okay, if these are y hats, okay, then the residual deviation becomes y minus y hat. Where are our y's? This is our y. We could have a y here. This is another y, the original point. This is the original point again when x is equal to 6. This is another point, y4, when x is equal to 8. And this is when x is equal to 10. This is our y5. So you could see that these points on the line here are what you call deviations from the y, or the given points y, okay, and you call them the residual deviations. And this is a more appropriate way of what do you call this, of getting or approximating the best fits or the best line for that certain scattered data. Okay, now to analyze how these deviations, residual deviations, fit better as a linear function for these given points, then we will have to evaluate. We're going to evaluate the squares of these deviations with respect to the mean and with respect to these residuals. Okay, so when we take the squares of the mean, okay, so remember this is our mean, this is y bar, and that's our mean, and this is equal to 16 sit-ups, right? And taking the squares of this mean with respect to the given points of the scattered data, you could see that the squares here are very much larger, and therefore when you say deviation, that's like, you know, moving away of the point from the standard or from a respective line which should represent the points. So as you can see, in this case, this is our mean, and the squares of the deviations from the mean are so large that they are not really a better, you know, approximation. The mean y bar is not a better approximation of or representation of the scattered data, right? Because the deviations are so large, the squares of the deviations are so large, and this creates a very big mistake when computing the y values, when comparing the given points to the mean. This gives us a larger squares of the residuals, right? But when we take the squares of the residuals as with respect to a given slanted line, you could now see that the squares are much smaller. So in this case, this is our regression line, okay, and that's what we modeled. And you could see that this regression line, as compared to the lines on the, or the points on the line itself, these are the points of the line, which are called y hat, and these are the original points. And taking the squares of the residuals, so you could see that the yield is smaller squares. Let us take this one for example. Okay, this is the square of the residuals. This is the square of the residuals from this point y hat and this original point. And this is the square of the residual between these 2 points. And also here, and also here. Notice and compare the difference between these squares. They're so large for the deviation from the mean, the squares of the deviation from the mean, which is called SSDev. And the squares of the residuals, which is called SSRes. Okay? Because we are so concerned with those, or the line which yields the smallest or the minimum square of the sum of the squares of the residuals, then that is the best fitting line. Okay? So let us go further into detail. And you can see that compared to the mean is here, right? At y equals y bar equals 16. Now comparing this mean value to the line, to the regression line, gives us an angle of rotation. And these squares of residuals, here, rotates into the regression line from the mean. Okay? So you can see that from the mean it rotates here and it rotates here. So that's the best, or the best fitting linear function using regression analysis. Okay?